Okay, hey guys, today we're going to be solving stoichiometric equations using a BCA table, or a BCA table before, change, after. You're going to need to do a lot of this during this class. So basically we wrote out the steps right here. 1, balance the equation. 2, convert the known mass to moles. 3, balance the equation. Use the balanced equation to set up the ratios, which is for C. Then use the approximate rho ratio to calculate the desired moles of the reactants or products, which is basically C to A. And then convert the mass to moles to grams to mass to, like, for here. Let's do this one. What masses of Fe2O3 and Al must be used to produce 150.0 grams of Fe? What's the maximum mass of Al2O3 produced? So what you do here, since it's given 115.0 actually grams of Fe, you just find the amount of moles, which is going to be 115 divided that by 55.85. You get about 2.27 moles. So that means, at the beginning there's always going to be 0 reactants. Then here it's going to be 0.27 moles. Then here, you don't know what that is. Then you just look. So what I did was I just looked at the ratio. So I know that for every 1 mole of Fe2O3, it's going to be 2 moles of Al, which means you need a lot more of this, which makes it limiting, and that would be excess. Limiting is all really most important part of this. All this is not. So what I did here was trace my steps backwards. So let's hear, I have 0.27 moles there. I have a 2-to-2 ratio there, which means I'm going to need 0.27 moles because of the mole ratio, because it's just 1-to-1. So if I know I have 0.27 moles here, excess is off. Then the change, you're just going to subtract 0.27 moles because limiting always goes to 0. So that means Al would have 0.27 moles. And then if you do 0.27, so 2 then for the Al is 26.98. 0.27 times 26.98, get about 7.3 grams of Al. Now you can use that to solve Al2O3. So it's going to be, right here it's going to be a 1-to-2 ratio. And always for the mole ratio of a BCA table, it's going to be the products over the reactants, which is pretty big. So if you're subtracting 0.27 here, you're going to do add 0.27 times that by 1/2, because that's the mole ratio. And to get that, so 0.27 divide that by 2, 0.135 moles of this. So if you know that the molar mass of Al2O3, which is about 26.98 times 2, add that to 16 times 3, it's going to be about 101.96. So multiply that by 101.96. So 0.135 times 101.96 equals about 13.8 grams of Al2O3. Now the bigger problem you don't know how many moles of this are, but it's excess, so that means it really doesn't matter for this. It's a 1-to-2 ratio, and it's always going to be excess over the limit. So which means it's just the same thing like you did here. So it's just that it's going to be 135 moles right there to react, because really it doesn't really matter for excess reactions. So molar mass of this one is going to be, let's add that to 16 times 3, 159.7. So when you do 159.7 times that by 0.135, you get about 21.6 grams Fe2O3. That's for the first one. That's like a harder BCA too. Now you have this one. If you were to react 52.9 grams of KCl3 with excess red phosphorus, that is red phosphorus, that's KCl3, what mass of P4O10 this could be produced? And since it gives you an unbalanced equation, you can stop right here and balance it out. When I balance it out, it's going to be 10 right there, 10, 3, 3, 10. So you have 52.9 grams of KCl3. So when you use your handy dandy periodic table, 39.10, that's at 35.45. Add that to 16 times 3. It's going to be 122.55 grams as the molar mass of that, but you only have 52.9, so 52.9 divided by 122.55 gives you about 0.43 moles. Then it says excess red phosphorus, which means that doesn't matter. Only thing that matters in these BCA tables are limiting. Then it asks for what mass of P4O10, which means it doesn't matter about that either. And since it's going to be a 3 to 10 ratio, but since this is going to be limiting, just subtract 0.43 first to get 0 moles because it'll just react completely. Then it's going to be a 3 to 10 ratio. Plus that there's going to be 0 there. So first you put the plus sign, then 0.43 there, times that by 3 over 10 because that's the mole ratio, is when you put it out in your calculator, times 3 over 10, 0.129 moles P4O10. But it asks for what mass. So first you'll have to just find the molar mass of P4O10, which is going to be 30.97 times up to 4, and that's 16 times 10. It's 283.88. So what you do is 0.129 times that by 283.88 grams per mole there. Those two cancel out. So when you do 0.129 times 283.88, you get about 36.6 grams P4O10. This is going to be a major thing that you have to do in this class. So basically, you can either do it the way I did, or you could just use the handy dandy steps, balance the equation, convert the known mass to moles, use the balance equation, set ratios, which would be something like that. And it's always going to be products over reactants or limiting over excess. Actually, yeah.